Hi everyone. This is a video about doing equilibrium concentration calculations, pre and post equilibrium calculations, which are essentially considered ice table type calculations. Basically, all these calculations share a common theme. The common theme is that given some information about the post-equilibrium condition, how can you relate that to pre-equilibrium conditions? So again, the way these all work, the way that they are all similar is that we kind of organize pre-exponential, post-exponential, the amount that the concentrations change in between those two conditions with an ice table, where ice stands for initial, change, and equilibrium. So I was going to work through a handful of examples where you show, okay, given that your initial concentration was something, what are the equilibrium concentrations? How much does the reaction shift? How much does it change in order to reach equilibrium? So here's a quick, here's a very simple example, or in terms of the structure of the reaction, a simple example, which is A in equilibrium with B. And since we will need some numbers here later on, I will tell you that the equilibrium constant for this reaction has the value of 5. So let's say you start with 2 molar concentration of A, no B. What are the equilibrium concentrations? That's what we'd like to know. Okay, so we'll set up our ice table. So we'll have one of our reactants A, our other reactant B, and we say, okay, let's fill this up with what we know and what we don't know. What do we know? We know the initial concentration, that's 2 molar. And even though it's not explicitly given, we also know the concentration initially of B. There is only A present initially. So there's no B. And then we can predict, okay, how does the reaction shift? How does the reaction change? Well, I have an excess of reactants and a dearth of products. So we know that we will lose reactants, generate products. The amount that we will lose or generate is unknown, but we know that they will at least be equal and opposite to each other, since it's a 1-to-1 molar ratio between products and reactants. So once they reach equilibrium, at that point you can just add these values together. You can assert that the equilibrium concentration should be 2 minus x and x. So these values we can substitute into our law of mass action and solve for x. Because the law of mass action tells us that the equilibrium constant, K, should be equal to concentration of B, which at equilibrium is x, over the concentration of A at equilibrium, which is 2 minus x. Again, that's going to be equal to 5. So now we're down to one equation with one unknown variable. That's something we can solve exactly. So I'll move over the 2 minus x, so I get x is equal to 10 minus 5x. So I multiply this over. 2 times 5 is 10. 5 times negative x is minus 5x is equal to x. So I can move the 5x over. So I get 6x is equal to 10. X is equal to 10 over 3. And is that it? Oh, no, what am I doing here? 10 divided by 6 is 5/3. So that's the change in the concentrations. Keep in mind, it's always good to remind yourself what physical quantity are you calculating? X in this case represents how much the concentrations changed. What we wanted to find was the equilibrium concentrations. So even though we've solved for X, the problem's not done yet. We still need to calculate these equilibrium concentrations. So those will be 2 minus 5/3, which is 1/3. And then X here will just be 5/3. So these are my equilibrium concentrations for A, and this is my equilibrium concentration for B. All right, so that's one example. I'm going to do a couple more that are similar, where the math gets a little bit more finicky. You need to make some approximations. So, similar approach here. So in this problem, suppose we have two hydrogen sulfide molecules reacting to form hydrogen gas and sulfur gas. And I will also tell you the equilibrium constant for that reaction is 1.6 times 10 to the negative 7. And yet again, I want to know what are the equilibrium conditions for all three of these chemical species once you've reached equilibrium. We want to know the equilibrium concentrations. Given that, oh yeah, I need to tell you something here. Given that you start with, did I say 0.25? 0.025 molar H2S. So you start with some hydrogen sulfide, the reaction occurs, you lose some hydrogen sulfide and generate products. The question is, how much? What are the concentrations of those chemicals at equilibrium? So, what we can do here is we can start filling up our icebox. So my icebox here, I'll have H2S in one column, I'll have H2 in the other column, and then S2 in my last column. I sometimes like to include the molar coefficients in my ice table just to kind of help remind me that they are there and they are important. What do I know? I know the initial concentration of H2S, so that's 0.025 molar. And yet again, even though the information is not given to you explicitly, implicitly, we know that the initial concentrations of my products are 0, because I'm not starting with anything. I'm only starting with reactant H2S. So then I can say, okay, I know the reaction is going to shift. Just like the last problem, it's going to shift to the right and produce more products. So I will lose reactants. I will lose 2x reactants. I will generate 2x hydrogen gas and 1x of sulfur gas. So again, we know you're going to generate some sulfur, you'll generate twice as much hydrogen, and you'll lose twice as much hydrogen sulfide. And again, those factors are coming from the molar coefficients in the chemical reaction. And then I can say, I can add these together and get my equilibrium concentration. So that should be 0.025 minus 2x plus 2x and x. These are my equilibrium concentrations, and I can plug those into the law of mass action and solve for x, figure out just how much of my reactants reacted. So equilibrium expression should be concentration of the hydrogen gas squared times the concentration of the sulfur gas over concentration of H2S squared. So I will plug those values in, so you get 2x squared times x over 0.025 minus 2x squared. All of that equal to K, which is, again, 1.6 times 10 to the negative 7. Okay, this is a case where we'll want to make an approximation. Why are we going to want to make an approximation? Frankly, because I'm looking at this and I'm thinking, okay, this is going to go as 4x squared times x. So this is going to be the cube, go as the cube of x. I need to distribute out this quadratic expression, and that's just going to make things much messier, for lack of a better word. So we can simplify some of this. So I can make a note that, so let me start this. I can say, okay, the numerator here should be 4x cubed. You square 2x, I get you 4x squared times x, I get you x cubed. And then I can say, okay, wait a minute, the equilibrium constant is really small. This reaction is going to heavily favor the reactants. Not a ton of products will be generated. If not a large number of reactants are converted into products, then I expect this value to be very, very close to 0.025. I'm subtracting a small number from a relatively large number. Something that's going as 10 to the negative 7 implies that x is going to be quite small, on the order of 10 to the negative 4 or 5. So I can say, okay, this should be approximately equal to 0.025 squared. So I'll lop off, I'll ignore that minus 2x, and I have 4x cubed over 0.025 is equal to 1.6 times 10 to the negative 7. So the rest of this becomes algebra. So what I will do here is I will multiply over the 0.025 squared, so I get 1.67 times 10 to the negative 4 times 0.0025 squared. I'll divide both sides by 4. That should be equal to x cubed. And then if I take the cube root of everything, I get that x should be equal to, what did I calculate here? 2.92 times 10 to the negative 4 molar. Again, what is x? X is how much the equilibrium concentrations changed. If you want to calculate the equilibrium concentrations, you still need to solve for them. So the concentration of the hydrogen gas should be twice this, so that ends up being 5.84 times 10 to the negative 4 molar. The concentration of the sulfur ends up being the same. It's 2.92 times 10 to the negative 4 molar. And then the equilibrium expression here, I'll just assert to you it's going to be about 0.025. So you can calculate that yourself. Okay. So let me try a third problem here where, we'll do, this will be just a little bit different. So let's say we have this reaction, which is, I'm going to make general here, which is 2A reacting to make 2B plus C, and I'll say that the equilibrium constant for this reaction is 1.6 times 10 to the negative 5. If I start with 1 molar each of A and B, what are the equilibrium concentrations? So we can approach this just as we've done previously by constructing our icebox, our ice table. So I've got 2A making 2B and C. So I know I'm starting with 1 molar A, 1 molar B and no C. So, immediate question is, how does the reaction shift? It's going to, again, shift to the right. Because I have no C molecules, at this point the reaction quotient is 0. So I know it's going to shift to the right and generate some products, generate some C. So I know that this is going to go down, the reactant's concentration will go down by minus 2x, the concentration of B will go up by 2x, and the concentration of C will go up by x. So when I get my equilibrium concentrations, those should be 1 minus 2x, 1 plus 2x, and x. Okay, so now I can plug these equilibrium expressions into the law of mass action and solve for x. So the law of mass action here should be that K is concentrations of B squared, so that's going to be 1 plus 2x squared times the concentration of C, so that's just x, divided by the concentration of 1 minus 2x squared. Again, this one's squared because, well, again, the law of mass action for this should be concentration of B squared, concentration of C over concentration of A squared. Okay, so now I've got one equation and one unknown, and yet again I'll assert that this is a quadratic equation which is not trivial to solve exactly. If you wanted to, you can work through all the algebra. I'm too lazy to do that, especially when I know there are approximations I can make that will get me sufficiently close to the answer that I'm looking for. So case in point here, K is yet again quite small. I don't expect to produce many products. I don't expect X to be that large. So what I can say is, okay, 1 plus something very small is about 1. So this is about approximately equal to 1 squared. 1 minus something small is about equal to 1 times x, well, that's still going to be something small, and that will again be equal to 1.6 times 10 to the negative 5. So then I can say, okay, x is 1.6 times 10 to the negative 5, and that will allow me to, once again, calculate all my equilibrium concentrations. So x here, concentration of C, should be 1.6 times 10 to the negative 5. This one is going to be around 1, and this one is going to be around 1. Because again, you'll be adding something quite small, and most of those insignificant digits are going to drop off anyway. So they should really be, if you want exact values, this one ends up being 1.000016. This one ends up being 0.999984. So again, about 1, and about 1.6 times 10 to the negative 5. Okay, so one more example, and this one is going to be this one is different. But we'll still use an ICE table to analyze the problem and construct a strategy for solving it. So this reaction, or this problem, we say, okay, suppose you have this reaction. Sulfur dioxide plus nitrogen dioxide is in equilibrium to produce sulfur trioxide and nitric oxide, and that the equilibrium constant for this is about 3. So this question is different in that the question is, how much nitrogen dioxide do you need to add to 2.4 molar, I'll just say molar here. You know what, I'll say moles, and then we'll assume these are all in a 1 liter container. So technically these should all be in terms of concentrations, but we'll assume the volume here is 1 liter. So we can just divide each of these moles by 1. That's fine. To 2.4 moles of sulfur dioxide, if you'd like to form, so to form 1.2 moles of SO3 at equilibrium. All right, so let me just run through that again. The idea here is you are starting with 2.4 moles of sulfur dioxide. You are going to add some nitrogen dioxide, and then the reaction goes forward. If you don't add any nitrogen dioxide, the reaction is not going to go forward at all. It's not going to shift at all because you have no nitrogen. You're missing one of your reactants, so there's no way you can produce any products. So the idea is you start with 2.4 moles of sulfur dioxide. You want to end up with, once you reach equilibrium, you want to end up with 1.2 moles of sulfur trioxide, one of our products. And the question is, given this is what you start with and this is what you want to end with, how much NO2 did you need to start with? I know it says add there, but the idea is you're adding it to this initial reaction mixture. So how much do you want to start with? So I'll set this up. So I have SO2, NO2, SO3, and NO here. So I know I'm starting with 2.4 moles of SO2. I don't know how much nitrogen dioxide I'm starting with. That is my unknown. That's what I want to determine. I do know that I'm starting with no products, so those concentrations are known. Then I know, okay, I'm going to start with some reactants, I'm going to produce products, so I will lose some of my reactants. So I don't know how much, so I will have a new variable here, y, and then I will produce some products. And then after equilibrium is reached, I have 2.4 minus y, x, minus y, and y, and y. So at this point it seems like, okay, if I were to try to plug in these equilibrium constants into the law of mass action, I would have k is equal to y times y divided by 2.4 minus y times x minus y. I know what k is. K is 3, has a value of 3. But this equation I can't solve just yet because it's one equation and two unknowns, x and y. So I can't solve that, except that we do know how much y is. We know what the value of y is because we know we want to form 1.2 moles of SO3 at equilibrium, meaning that at equilibrium, SO3 should have 1.2 moles produced. So that means y actually is known. Y is equal to 1.2. So this is going to be 2.4 minus 1.2. This is going to be x minus 1.2. And then when I substitute all these values in, so I have 1.2 times 1.2 divided by 2.4 minus 1.2 is 1.2 times x minus 1.2. All of that equal to 3. So my problem now becomes, okay, these 1.2's will cancel. My problem now becomes 1.2 divided by x minus 1.2 is equal to 3. Solve for x, where x will tell me how much nitrogen dioxide I want to start with. So if I move over, I'm going to move this over here. If I move over the x minus 1.2 and divide by 3, so I got 1.2 is equal to 3 times x minus 1.2. If I divide by the 3, so I have 1.2 divided by 3 is equal to x minus 1.2. Add over the 1.2, so I have 1.2 divided by 3 plus 1.2 is equal to x. And then x is, if I calculate this, I get 1.6. So I need to start with 1.6 moles of nitrogen dioxide. Okay, so those are a few different examples of how you use an icebox to sort of structure what you know about an equilibrium system, or a system that was at some point reaches equilibrium and at some previous point was not at equilibrium. An icebox is a great way to organize what you know, what you don't know, and what you want to find. So I've given you a few different examples of doing that. If you have any further questions, please come see me in my office at any time, and I will be happy to work through some practice problems. Otherwise, I will see everybody later.